Good morning and welcome back to Dr. Logic Does Logic in the only room in the house quiet enough for recording videos right now. I received a really interesting and very good question about some of the proofs of soundness that I gave in the most recent videos, particularly the one for negation introduction and conditional introduction. And the question was, why are we allowed to assume that the subproof that we are doing is sound simply because it is less complex from the larger proof that we are working in? And this is something where it was a good question because I didn't explain it quite as clearly as I probably could have in the context of the videos. So I'm going to talk just about that right now. The idea comes from the structure of the proof. So when I say proof here, I'm talking about the argument that I'm giving. So it's a meta-language proof rather than the object language proof. But it's a particular type of proof mechanism or proof technique called proof by induction, sometimes called proof by mathematical induction, particularly when you're using it to prove things about numbers. The basic idea is that if you can show that some property or some fact holds of a starting point, so if we're talking about numbers, this would be like the number 0 or perhaps the number 1, depending on where you want to start counting. And then if you can also show that if the fact holds of all numbers, or say all proofs, up to a certain point, then if you move one step on, the fact will still hold. So proofs of this nature come in two parts. The first one is the base case, where you simply show that the fact holds of your starting point. And then you have the inductive case, or the inductive step, where you say, suppose that everything has gone well up to now, then if I do one more step, things will still be good. I'll still get the desired result that I want. And then if you can prove those two things together, you can then conclude that your result holds for everything in a particular set or a particular context. So just to give you an example with numbers, suppose that I wanted to prove that every natural number, so every counting number, 0, 1, 2, 3, etc., is either 0 or the successor of a number, so something that comes after another number. What I would need to do is first prove the base case, prove that 0 is either 0 or the successor of a number. Now, that's going to be easy because 0 is 0 by definition, therefore 0 is either 0 or whatever else. Then I would want to show is pick an arbitrary natural number, n, and then assume that every number up to this point, including n, is either 0 or a successor. Then, if I can show that, with this assumption, the next number in the list, so n plus 1, is also either 0 or a successor, then I can conclude that this will hold for every single natural number. Because if it holds for 0, then kind of the first inductive step would be, well, if it holds for 0, then it holds for 1. Okay, it holds for 0, so I've got this, if it holds for 0, then it holds for 1, so I know it holds for 1 as well. But I can also show that if it holds for 1, then it holds for 2. But I know it holds for 1, so it also holds for 2. And if it holds for 2, then it also holds for 3, etc., etc., etc. This same sort of structure actually works with proofs, in part because we number our lines. So we can say, well, okay, basis case are assumptions. What we are trying to show is that if all our assumptions are true, then every rule, every line in the proof that comes after will also be true. Well, if all of our assumptions are true, then all of our assumptions are true by definition. So the base case of these sorts of proofs often just comes from the definitions. Therefore, we just kind of ignore the assumption rule because we kind of get that for free and move on to the more complex rules, the ones that are actually allowing us to make new lines in our proof. So what we're trying to do is show, it's like, suppose everything we've done so far was truth preserving, then one more step is not going to make it not truth preserving. Another way to think about this is that if you have a proof that is unsound, then there is a first move that you made where things went wrong. And so suppose that I apply a rule in my proof and I'm moving from like line n to line n plus 1, If I'm not assuming that everything I've done so far was good, then finding out whether this step is good or not doesn't really tell me anything, because maybe the problem was just earlier in the proof. In that case, I shouldn't be looking at line n. I should be going back up earlier in the proof until I find that place, that first place where I think that things have gone wrong. So this is why we always assume that everything that we've done in a proof up to the step that we are interested in is sound, because it allows us to essentially identify the first place where things could go wrong. That means that if we have a subproof within one of our proofs, we will assume that we actually applied every rule correctly in that subproof. Because if we hadn't, then why are we looking at the bigger proof at all? We should be looking at the subproof and trying to find out where the error is there. So this is basically a more detailed explanation of how this sort of proof argument structure works and why we are able to use it in order to prove the soundness of propositional logic. So I hope that was helpful, and I will happily answer any other questions that you have. If it's something easy, I'll just answer in the comments. But if you've got something more substantive and you're like, I'd really like to know more about whatever, let me know. Happy to record a video. Take care and see you next time. Bye.